Good afternoon, everyone. Are you guys working already on project number, what is it? Seven?
Trying, I can't.
What's the problem?
So I guess I got to the point where now I've extracted the 20 points that go from 400 to 1800.
Okay.
And so now I've put them into MATLAB and I've converted my depths so that they're peak because I was using peak because that's what
Okay.
were initially given in. And so now we're being asked to make the plots using the porosity and void ratio. And I
Yes.
wasn't sure how to use what we had to make plots. Yeah, to find that relationship and to create these plots. Because when I just put general pore pressure and vertical
Um,
stress.
so here the two variables are on one side porosity and also effective vertical stress, which you know those two.
Right.
So the only thing that you have to do here is you put sigma v here, porosity, and your data is going to look something like this.
Okay, I guess mine kind of like.
But up to here, right?
Yeah.
So just that one, where sigma v is v minus pp, and it should look something like this. If it doesn't look like that, then there is a problem with the effective vertical stress. And after you do that, you throw a line. What that line is going to be one of these equations, and out of here you're going to fit two parameters, either this one and that one, or this one and this one. So for each one there are two parameters that you can get out of here. So basically these are going to be the models, and here you have the data, and you have two fitting parameters for each one.
Taking off of that.
Yes.
Graph. Those are all pore pressures.
Which ones?
We're directly graphing the porosity.
This is directly porosity.
Theta. No, wait. So those aren't theta values. Those are.
This is just porosity.
Okay, what symbol is that?
This is porosity. Yes.
Okay, yeah. And so we're just plotting those.
Yes.
Okay.
So I think there is some issue here. I think there is one missing line over there. Or I don't know if this is logarithmic scale. It might be logarithmic. Please check original reference. Make sure you get the right porosities. It could be logarithmic scale. Yeah, you're right, Rodrigo.
And so that means that the furthest most point is 0.1 and
This one will be 0.2 and 0.3.
and so it's
Yeah, I think that's what it appears to be.
okay. That's what I thought.
Yes. So in the web appetizer, you can also set the logarithmic scale.
I saw that and I wasn't sure, so I assumed it was linear. But
Okay. Anything else from here? Yeah, just to further continue with that, if you take the natural logarithm of this, of the first equation, it should be natural logarithm of porosity divided reference porosity. That's going to be equal to negative v sigma v divided by 1 MPa. And the slope of this line, this beta, should be that slope over there. So that's what this looks like, a line. So if sigma v were to increase linearly with depth, then you should expect all the points to fall in a line. But since here there is a deviation, they don't plot on that line. But up to here, they more or less do.
So beta is the slope of that.
If you had an axis here of sigma v,
Okay.
and if you had this one in log scale,
Okay, so if you went porosity log and cross and sigma v down,
yeah.
then the slope of that would be beta, and then we could solve.
And also, well, what I would say, it's just going to be easier to either if you use a linear scale or a logarithmic scale, just get the data of porosity, plot it in linear scale and sigma v. This should look a little bit concave, and then use these two equations to fit that data.
Oh, so go through and change.
Do that. So you can use, if you're using Excel, so that allows you to calculate values in order to minimize an error.
Oh, okay.
So there are two ways you could do this. Also, if you linearize this problem, you just have to throw a regression line. For example, if you were to do a plot, well, okay, but you don't know this one, right? So, okay, if you were to linearize this problem, this would be natural logarithm of porosity is going to be equal to natural logarithm of reference porosity minus b times sigma v divided 1 MPa. And this will be like your, let's say, your y. This is going to be your x, and these are going to be your parameters a and b of a line. Or you can also use solver. It's not too difficult. The only thing you have to do is just propose some values, compute what the values would be, calculate the error between that and the theoretical prediction, and the actual value with the theoretical prediction, and then you tell solver to minimize the error by changing the two values, which are the parameters. Rodrigo, you have a question?
What would be the reference porosity? Is this the shallow porosity?
In this case?
Yeah.
In this case, the reference porosity would be the porosity that you get when sigma v is 1 MPa.
Okay. So it's like the shallow porosity?
Not necessarily, no.
Okay.
No.
Okay.
No, it's something that you have to, it's an unknown. You have to calculate it. It's going to come from the curve fitting. Okay, so I hope that with that, then you can solve the rest of the problem. And the second part is going to be to utilize this elastoplastic model to calculate elastic and plastic deformation. And that's what we're going to see right now. Okay, so last time we discussed about putting together now the deviatoric stress, the isotropic stress, and it's more or less the same thing, but differently. And the concept was that your material gets stronger. And the relationship between how much stronger it gets and at what porosity you get that strength depends on this isotropic consolidation line, which is this line over here, and simply tells you what is void ratio or porosity as a function of the mean stress. Okay, so we're going to follow that in order to predict first elastic strains and then plastic strains. What we're going to do is, our final objective is to be able to predict elastic strains as we go before the yield point and plastic strains as we go over the yield point. And the project asks you to calculate something like this, and you will see how with the equations that we're going to see, you're going to be able to do something like this with the strain nicely rolling into an asymptotic value when it reaches the critical state line. Okay, so let me summarize this with the equation. At the end of the day, all what we want to do is to calculate the total strain, where the total strain, as we assumed before, is going to be the summation of the elastic strain and the plastic strain. Now, this is going to be a process which is non-linear. And because it is non-linear, we cannot add elastic strain and plastic strains at any time. So we're going to have to do this in parts as a function of time. For each time step, we'll check if there is either an elastic strain or a plastic strain, and we'll add that according to a given time. And because of that, what we're going to do then is we're going to calculate incremental changes of strain that are going to be the summation of incremental changes of elastic and plastic strain. The first thing we're going to do now is to calculate these incremental strains of elastic strain. At the end of the day, these incremental changes of elastic strains, as we know from before, for the elastic part will depend on an elastic stiffness matrix times a change of stress, and the plastic part will also depend on a matrix, but now this is not going to be an elastic matrix anymore. It's going to be a plastic matrix times an incremental change of stress. In general, all the elastoplastic models, they follow this equation. We're going to see what this equation, these matrices look like for this Kampf-Clay model. All right, so let's go first with the elastic strains. For elastic strains, for this particular model, we cannot use linear elasticity because this model goes a little bit beyond linear elasticity and assumes a non-linear deformation. If you remember, we talked about compression curves or compaction curves in which if this is the void ratio, which is proportional to porosity, and this is the natural logarithm of the isotropic stress or the mean stress, it should be the mean stress. This is the mean stress, P prime, mean effective stress. We said that we can load the material, and if we get before the yield point, this deformation is going to be elastic. And the slope of this line, if this is equal to 1, we're going to call it kappa. Please remember that this is what is almost exactly the same to what we discussed before with the compaction curve under one-dimensional strength condition, where we have unloading and reloading, and then after loading, now we are on this part of the curve before the yield point. And this one is exactly the same, but I'm going to draw this line, but we're not going to use it right now. After it gets to that point, we get into the plastic part. But we're not going to use it now. It's just a compaction curve, but for this one will be under isotropic loading. Okay. So what this line is telling me, and because it's as a function of the logarithm of the mean stress, is that void ratio is equal to a constant, that doesn't matter now what the constant is, minus the coefficient kappa, which is the slope, times the natural logarithm of p prime. It's just a equation of a line. Okay, so we want to compute strains. Remember that that's our objective, okay? So we're going to go from void ratio. Our objective is to get to volumetric strain. Void ratio, at the end of the day, it's a measurement of porosity, so we'll be able to do that. The differential form of this equation would be equal to this, because we have a logarithm over there. Okay. Now, void ratio. If you remember, void ratio is equal to the volume of the voids divided the total volume, or the bulk volume, minus the volume of the voids. What that means is that you have a variation of the void ratio. This is going to be equal to a term that depends on, we have two variables, a variation of the volume of the voids plus a variation of the bulk volume in general. Here you can work with this equation and tell me what that is, but it doesn't matter for this purpose. What is important here to know this is that what we're going to assume is that for this type and for this model, the variation of the voids, or the pore space, is equal to the bulk variation. What does that mean? Okay, right? And therefore, it assumes that something is in. It assumes equilibrium? No. Well, it could, but that's not where I want to get to. Which phase is incompressible according to this assumption? The grains are not compressible. So this assumption does not take into account pore elasticity, and it usually works well for soft sediments in which all the loss of porosity transforms into volumetric deformation. We are not accounting for the compressibility of the grains. So you could say in this case, alpha, the poroelastic coefficient is equal to 1. Okay, so doing this assumption, now we can, and noticing that, let me go in this direction, noticing that a variation of volumetric strain is going to be equal to a variation of a bulk volume divided the initial bulk volume. Together with this equation, what we're going to obtain is that the variation of void ratio, this is just playing with derivatives, we don't have to do that, but just let me write the complete equations for the sake of completeness, is going to be -1 plus the void ratio times the variation of volumetric strain. And this is the relationship between void ratio and variation of volumetric strain. So we already have the volumetric strain. And using this equation and knowing this relationship over here, so let's call this one 1 and this one 2, 1 plus 2, we can write that the variation in isotropic component on the elastic part is going to be equal to K, or kappa, this is the kappa, it's not the K, divided 1 plus the void ratio times the variation of the mean stress divided mean stress. So now we have a relationship that tells us what is a change of volumetric strain due to a change of mean stress at a given mean stress. And here this is very important because it's not the same if you are here than if you are there. Over here, it's a lot more compressible than over there. So this value, it's important. Okay. And this is for the elastic part of the isotropic component. And then for the deviatoric part and the elastic part, we're just going to use what we were using before, that the deviatoric strain or a shear strain is proportional to the shear modulus. And this equation is going to look like this. 3 times the shear modulus times dq, and this is going to be, I need to define here what is this is a shear strain or a deviatoric strain. This deviatoric strain is equal to 2/3 of epsilon 1 minus epsilon 3. This 2/3 comes from isotropic conditions and summation of strains. And notice there is a 2 here. You remember that for shear strains we have 2G. Well, that 2 is going to cancel out, and at the end we're just going to have these 3 over here. And at the end of the day, we're just using a shear modulus. So we're assuming that the deviatoric part, the elastic part, is linear, elastic. The volumetric part is elastic, but it's non-linear because we have a logarithm in there. And that is capturing, again, the fact that the rock tends to be a lot more compressible at low stress than at high stress. A very similar thing happens with fractured media. Fractured media tend to be a lot more compressible at low stress than at high stress when the fracture starts to close. You can also write the same equations of compressibility with this logarithmic function. Okay, so now the only thing left to do is to see what is this stiffness matrix. And this stiffness matrix, we're going to write everything. The strain is this. Let me ask you the following. In the equations that we have evolved, are the volumetric strain and the deviatoric strains coupled, or do deviatoric strains or does a deviatoric stress cause a volumetric strain? No, right? And the opposite is also true. A change of mean stress does not cause a deviatoric strain. So
you said, does a deviatoric stress change volumetric strain? And the answer would be yes, right?
it would be no. It would be no.
Because, well, so how is volumetric strain? Aren't we talking about the volume of something?
Yes.
You apply a deviatoric stress to it. Well, I guess it's.
So, well, if you change the volumetric, if you change the deviatoric stress, but the mean stress doesn't change, then you're not going to have any change of volumetric strain. So it's a little bit more obvious from the equations that you see that in this equation there is no Q, and in this equation there is no P prime. So as long as you keep P prime the same, if you change the deviatoric strain, say you make one stress larger and the other one smaller, but at the end of the day the mean stress is the same, volumetric strain should not change according to these equations.
A somatic thing, because it's deviatoric strain that changes.
Yeah, probably when I was saying this I mixed up what I was trying to say, but remember, these are
You said it right.
strains. Sometimes, you know, these get mixed, and this is stress. So changes of deviatoric stress will not cause changes of volumetric strain. So these two are zeros in this matrix, and here I have just this kappa divided 1 plus the Boyle ratio, and also I have here, actually I have this one and P prime, and here I have 1 over 3 times the shear modulus.
Why the deviatoric strain is not weighted by the void ratio also? I mean, because in the first equation we had void ratio weighting
This one?
the mean strength, yes, and in the bottom one you do not have it. You only have the shear.
Yes.
And why is that?
So this one comes from this equation over here, and from this one over there, from this one over here, from these two. And the volumetric strain can be related to porosity, but the deviatoric strain or a shear strain is not related to porosity. You can shear a porous medium as long as that shearing is small. The porosity is not going to change. It doesn't have to change. You're just applying shear. You're applying distortion to the medium. You're not applying a change in porosity. Probably what it's making this a little bit confusing is that we are still in the elastic part. We are not in the plastic part. The plastic part, where we're going to get now in just a bit, is where you start to have these things, where now deviatoric strains are going to cause volumetric strains. But we didn't get there yet. Now we are inside here, and we just have elastic strains. And the same thing as we had before for linear elasticity, in which we said that the shear stress will not cause a change of a normal stress. Here in the elastic part is going to be the same. These two are not going to be coupled. They are not going to they are not going to bother each other in terms of causing strains in other direction, because we are still in the elastic part. So remember, this one is for the elastic part before yield and before grains start to crash or grains start to roll on top of each other. There is one more thing I want to add over here. You will see in the equations that I put in these equations that there is one more parameter, this parameter V, and that's something called specific volume. I just didn't want to add one more parameter in my equations here, but 1 plus void ratio is this specific volume parameter. Okay, so one more time. In the elastic part, shear and mean stress are not related. They do not cause strains to each other. Okay, so we have the elastic part. Now we can predict strains before the yield point with this model, and now this is a nonlinear model. Linear shear or deviatoric strain. Okay, well, let's say that we get to the yield point now. How do we continue? Again, there are going to be two parts. The volumetric part and the deviatoric part. When we get to the yield point, if we're just doing a simple compression, when you get to that pre-consolidation stress, your material is going to start deforming at a faster rate than before for an incremental change of the logarithm of stress. And this new slope, lambda, is going to be higher than k. So this is going to be elastic. And for example, we could assume if this is going in this direction, we could say this is loading. This will be elastic loading. When we get to here, we are continuing loading, plastic loading. And what we're going to assume is that when we do unloading, we come back at the same slope kappa. So this will be elastic unloading. Okay, but now we have the component in the plastic region. This would be the point in which, for example, you start to have grain crushing, or where you start to have pore collapse. You go over the maximum stress. This stress is very important because many times that stress is also known as the maximum let me remember the name for the, I know in mechanical terms it's a pre-consolidation stress, but in geology it has another name. Is the, I don't remember if it's the historical burial stress or the maximum burial stress. I'll remember, okay? But it's something like this. What that means is that sometimes you can have rock which is deposited and you have a lot of sedimentation and you get to a maximum historical stress, but due to exhumation and erosion of some layers, the rock can get unloaded. And as it gets unloaded, it gets pre-consolidated or pre-compacted at a higher stress. There are some rocks that are at the current maximum stress that they have seen throughout the entire life. There are some other rocks that have seen higher stresses, but due to erosion and exhumation, now they are subjected to lower stresses. So in some of those rocks, if they have a higher historical stress than what they are currently now, then usually you go through an elastic region. If they are currently at the maximum historical stress, they will be over here. So if you continue loading, you will go this way. Okay. And we are okay now with the elastic part. Let's see now the plastic component, which is going to be a little bit more difficult. Okay, for the plastic strains, we're going to invoke again the yield surface, because the yield surface is the one that is going to tell us what those changes of strain are going to be. And this is something like this. If you remember, the yield function or the yield surface is this ellipse over here and this equation of this ellipse, where our objective is to obtain a vector perpendicular to that surface that is going to tell us what is the change in plastic strain. And this is going to depend on two components: the change of plastic strain on the volumetric part and the change of plastic strain on the deviatoric part. For example, when we are at this point, the vector is just normal to here, and we just have volumetric component. There is no deviatoric component. When we are at the critical state line, we have just a deviatoric component. This point, you could imagine this as, for example, two masses of rock sliding to each other, respect to each other, without any change of volume. It's just a sliding. It doesn't, as it slides, the blocks do not get closer, they do not get further apart. There's no contraction, no dilation in the plane of failure, just slides. next to each other. That's the case of perfect plasticity. And again, here it will be just volumetric strain. Okay. So let's use an alternative version of this. It's the same thing. I'm just dividing by the pre-consolidation stress. This is an M, by the way. My M's look like pi or something like that, but that's an M. And we're going to make these equations a little bit shorter by defining this parameter eta, which is basically the ratio of deviatoric stress to mean stress. If we do a little bit of math, if you remember, the flow rule requires to calculate derivatives. And these derivatives are going to look like this. We have 3 derivatives. Remember that the pre-consolidation stress is a variable. As you load the material and you reduce the porosity, it gets stronger. And this is going to be P naught M squared I think I tried to do this one time. Took me entire afternoon to do all these derivatives. But here we just have a summary. And the last one, all right, so we have the derivatives now, and if we apply the flow rule, in this case, we're going to apply the associated flow rule for this part of the yield surface, and that flow rule tells you that the variations in plastic strain in a given direction, that's what that means, that this ij, for if say epsilon 1, epsilon 2, epsilon 1, or as we are working now with, instead of those, we're working with more like invariant strains, epsilon p prime and epsilon q. This is going to be equal to a parameter that we'll see what the parameter is times the derivatives with respect to stress. And from here and from our previous derivatives, we get that the isotropic or the mean, the volumetric strain is going to be this times what we have above with the variation of the mean stress, and for the plastic strain, this is going to be that again, but with a variation of the deviatoric stress. Okay. So I know what that derivative is. It's over there. I'm not going to write it again, but I can put this one next to that one, and I can get the value of the plastic strain. So this is the volumetric strain, the volumetric plastic strain, and it's going to be this parameter times that at the yield surface. This is just from the flow rule. But I have another piece of information. Let's call this one 1. Well, let's call it 3. And I have another piece of information from the isotropic consolidation line, which is this one, and from the isotropic consolidation line, I know that a change in plastic strain in the volumetric component is going to be equal to, let's say, if I go from here to there, now I have to use lambda instead of kappa, right? But if I take into account kappa and lambda together for an elastoplastic process, then similar to, where is that one? Similar to this equation, I'm going to have that the plastic volumetric strain is going to be equal to lambda minus kappa divided 1 plus void ratio is the same thing as this other one over here times a change in mean stress divided, actually it's a change of in the pre-consolidation pressure divided that pre-consolidation pressure. That would happen when I get to the yield point and I change this value. This is what is going to be the plastic strain. This amount comes directly from that plot. And having now this one and this other equation that I have over here, you see that in both of those I have a volumetric plastic deformation. Then from this one I can obtain that this parameter d psi is going to be equal to, just by equating those two equations, 1 plus void ratio p prime m squared plus eta squared. And this was the link that we needed. This is what is called the hardening parameter, and will tell you how stronger the material gets when you have a volumetric plastic strain or a change of porosity. Yes, Jack.
I thought from the graph PO prime is constant.
No, it's not a constant.
So it changes.
Yes, because, for example, when you go from here to there,
From PO prime to that point, okay.
yes, and you unload, now this is going to be the new PO prime. Do you see that or not? Probably it's a little bit easier to see in the linear plot. This is like this. Imagine that you have a sediment, a rock, and you start to load it. This is what is called virgin compression, and you have plastic strain. Then you unload it. The maximum stress that the rock has seen is now this value. So it will be elastic till you get to that value, and then we'll jump again onto this compression line, plastic line. And then you can load it up to here, and if you unload, the new maximum compression will be this one. And you can reload it, and if you don't achieve this value, always you're going to be in an elastic regime. But if you get to here, you get once again in this line. And this is what it makes your yield stress, your yield surface to move. So this P naught is not a constant, it moves.
And just to clarify, for those two unloading cases,
Yes.
are the slope the same or different?
For which ones?
For the one you just showed, you showed two unloading cycle, right? For the graph.
Here?
No, the other one. The other one you just showed.
Here?
Yes. For
So,
the two unloading
well,
axes.
these axes are linear. So, and remember, this is a non-linear deformation. Rock is more compressible here than over there. And the compressibility is not the same.
Okay.
But when you put this into a logarithmic plot, the slope is the same. It doesn't mean that compressibility is the same here and there. But the compressibility normalized by the logarithm of stress is the same.
I know it's kind of far back. Can you explain equation 2 again? I don't know where that comes from.
Equation 2?
Yeah.
Let's see, what is equation 2? This one?
Yeah.
This one is just by taking derivatives.
Right.
What is the derivative of this one with respect to void ratio? Or you could say, what is the derivative of void ratio with respect to elastic plastic strain? Well, here you have the definition of elastic plastic strain, and here you have the void ratio. So let's see. This is equal to, I don't want to get in these rules of derivatives, because basically what you have to do is you have to take the derivative with respect to this one.
Okay.
And then replace this in terms of that, and then you will obtain this. It's just rules of derivatives.
Where did that middle, the equation to the right of equation 2, where did that one come from?
Which one?
Keep going.
This one?
Yeah, with that.
Okay, this one is just a definition.
Oh,
Notice that
changing. Oh,
this is changing volume. This is volumetric strain.
over
Changing bulk volume divided bulk volume.
all the original volume?
Yes. And because we have assumed that change of bulk volume is a change as the volume of the pore, this is just porosity, or change of porosity, actually. This is change of volumetric strain, or change of porosity. But this is just a porosity. Okay. Our objective now is to get a similar matrix for the plastic part. And we have the equations, so we know what these derivatives are.
Can you remember what is F again?
F,
Yeah.
F is a yield surface.
Yield surface, right?
And F star is the new yield surface?
It's the same yield surface. It's just the yield surface expressed a little bit differently, equating some terms.
Okay. Oh.
But it's the same thing. It's exactly the same thing. It's just a more convenient form to express all of these equations. Okay, so let's zoom out from here. These are the flow rule equations. We know what the derivatives are. We know what the hardening parameter is. So we have everything we need. We just now need to put this together. And this is going to be the plastic volumetric strain and the plastic deviatoric strain is going to be equal to the hardening parameter I'm going to put it the same as in the in the equations I gave you using a specific volume, but it is just the hardening parameter. That's going to be the common factor times now these derivatives. And in these derivatives, notice that, for example, for P, we have both Q and P. And for Q, since we have this eta here, also we have both Q and P. So now, opposite to the elastic matrix, the plastic matrix is going to have elements which can produce, for example, let's just look at the volumetric strain. The volumetric strain can be produced by changes in mean stress, but also by changes in deviatoric strain. Now we are in the plastic part. This matrix is also going to be symmetric, and for the deviatoric part, we're going to have that the deviatoric strains can be caused by changes of mean stress and also by changes of deviatoric stress. And these are going to be the plastic strains. And now is when we are in the plastic part that we start to capture. Where is that? Here. That we start to capture this part, at least for this part of the yield surface. That we can have simultaneously cause to, for example, shearing. We can also have volumetric compression or change of porosity. Or over here, if we have dilation, if we have shear and have dilation, also that's going to affect volumetric strain. And that's captured now in these two terms, which are the off-diagonal terms of this matrix. So at the end of the day now, basically what you can do is, and what we're going to have to do in the project is going to be, let me see, I don't have any more paper. Anyone has paper? You do?
Yeah, I do.
Okay. I think I need about two blank pages.
I was inspired by
Okay, thank you. Yeah, I think I just need two. I think it should be right. I'll ask you one more if I need. Thank you. Okay, so in the project, what you're going to have to do is you're going to have to predict what is the response of an elastoplastic material that undergoes triaxial compression and that's going to go through this part of the yield surface. So you're going to start somewhere over here, and in the elastic part, it's very simple. It's just it's non-linear. Be careful, okay? But you could go, if you know the stress path, which you know because it's going to be a line with a slope 1 to 3, you could check which is this point, and from here, from the elastic part, and with the elastic matrix, you are going to predict what is going to be wait. No, this is Q, and this is EQ. You're going to predict what is going to be this elastic part up to there. And after you get to the yield point, you're going to have to break this stress path into segments. Probably with 10 will be enough up to that point, where that you know also where it is, in order to predict small changes. So let's say that you do this, that, you should get something like this. So you fix what your dq is, and also your dp, and you calculate what is the additional change of strain. And all you need for that is just the matrices, define what is dq and dp, and that's it. Where, yes, I can. Well, remember, dq is going to be equal to 3 times dp prime. This is a axisymmetric triaxial stress path. Let me think about that. I'm just going to do the same thing, but in color, because there is something I want to add over here. I think I'm running out of ink, running out of paper. Okay, I think I recovered. Okay. All right, and that's the end of that project. Do you have any question? Again, it's just incremental changes of stress. You calculate incremental changes of strain, and you will obtain something like this. Okay, let me drink a bit of water. All right. Let's see something now conceptual, which is very interesting, and it's very important, I think, to know. And it's related to something which is called strain localization. We called this strain hardening because the more strain you put, the stronger it gets, or the harder it gets. That's why it's called strain hardening path. We also saw that for the same material, if you start at a relatively low mean stress, this is going to be something like this, and this is a stress path. It's going into this direction. This is going to go into, let's do it, into this direction, but then it's going to come back eventually into that critical state line, and the effect of that is going to be that up to this point these are going to be the same, but then this one will start dilating, will reach a peak, and will eventually go into an asymptotic value of Q. And this one is called, again, strain softening, because as you apply more strain, it gets softer, or the stress gets reduced. This point is what is called the peak stress. And yes, this one will be the peak stress, and this one is what somehow or sometimes is called also as residual strength, because it's what you have left after it might break. Yes.
So this is for hard materials, not like soft sediment?
Well, you know, anything could be this and that. It depends what is the mean stress. For example, let me see if I find a picture quickly of a good example that a colleague of mine sent me some time ago, and it's a great picture. Let's see. I cannot find it on my phone. Let me try one more time. I don't remember if I saved it into my phone, but just give me one sec. I'll see if I found it. I know I have it on my laptop computer, but don't remember if I have it here. Okay, I'm close. Just one sec. I have a picture with Larry Lake here. I don't know if you're gonna see. No, I don't have it. I'll owe you that picture, but I'll try to find it. And this is a picture that shows, for example, how a relatively brittle material like marble can be strain softening, have a very well-defined peak, and also be strain hardening. It just depends on the mean stress. And there are also some other variables that affect that. Like, for example, probably this is a good point to talk about this. We said that materials that go, wait, let me say that later, because I don't want to, I want to make a very good point over here, and then I'll go through that. But that's called brittle to ductile transition. And it depends on mean stress, but mean stress is just one of those variables. Temperature, for example, also produces this variation. Okay, but let me tell you what the point I want to make over here. It's very interesting to see how these materials will distribute failure as they go through this process. For example, let's think on a strain softening material. And let's divide the rock into sort of small grid blocks in which now this rock is a real rock, and not all the grid blocks are exactly the same. They don't have the exact same strength. So when you load this rock, at some point, somewhere inside the rock, you will have these stresses, deviatoric stress, mean stress, but there's going to be some point which is going to be the weakest within this sample that it will fail. And let's say it's that one. Okay. When this one fails, that means that that piece of material took the largest stress possible. And after it takes the largest stress possible, because this is a strain softening, after it fails, it won't take such a high stress anymore. And the result of that is that because this element doesn't want to carry any more stress, such a high stress, because it already broke, which elements do you think are going to take that stress? The surrounding, the adjacent elements, because once this releases the load, the elements next to them, they have to take it. But the issue of that is that probably now, if those were very close to peak stress too, and then you give them additional load, are going to break too. And when they break, they will also go through this strain softening process, and they are going to say, I'm not taking this load anymore. And it will be passed to the next one, and the next one, and the next one. And this is going to form a well-defined failure surface, because the failure is propagating adjacent to the elements. And here I'm drawing these ones sort of at an angle because I'm trying to emphasize that this is going to be a shear failure, and that's why it is at an angle. So, and this is just going to stop whenever the material completely fails. But this is what is going to be a phenomenon of strain localization. Basically, here we have something which is called a positive feedback mechanism, because once break, it makes the other one break, and the other one break, and so forth, and that makes this fracture to propagate and to localize. One more thing here is that this is sort of an unstable process, meaning that when you get to the peak, there's no way to get back, because this fracture is going to propagate very quickly, and you will never be able to recover that failure or recover that surface. Of course, it's a plastic deformation, so you cannot recover it, but just going to roll down this strain curve. Let's see what happens now with the other case, with strain hardening. Let's make the same grid blocks. Oh no, you know what? Now I remember, I think I deleted that email. I'll try to find it. Okay. In strain hardening now, when you get to yield, thinking again that this is a heterogeneous rock with some small variations in strength, there is going to be some part of the rock which is going to fail. Let's say here. Okay, but notice what happens now. This part that failed first because it was the weakest, when it undergoes some plastic deformation, gets stronger. It doesn't get weaker, it gets stronger. So if it was carrying some load, it will continue carrying that load to the neighbors and but everywhere else in the rock also this is going to be loaded. So probably at some other point you will have some other point that gets into yield and gets stronger, and then another point. Probably after that point, if this were to be a correlated field of strength, probably you will have some other element over here that starts to take some failure, but they always get stronger and stronger. And as a result, you're going to have a diffused failure which is not going to be localized, but is going to be distributed all over the material. There's going to be a point at which probably all the rock is going to get into plastic strain, and probably that will be when you get mostly around here. But now by failing your material, you have distributed strain, and as a result what you see is that sometimes you get like these tiny shear bands that are not localized into one particular region but are distributed all over the sample. And this is when you get shear, let me write it here, shear and compaction bands. And opposite to the previous one, this is a stable process, and opposite also to strain softening, now you have diffuse deformation. Let me try to see again if I can find a picture. Okay, any question? No.
So what is the shear band?
The shear band is going to be a location in which shear and compaction happen together, and it usually also it might localize in some areas. Yes, when you get to this point.
Then what?
At that point, it doesn't harden anymore, but it just deforms in with just a deviatoric stress, with deviatoric strain, sorry.
And for the numerical simulation, is there a continuity on the boundary between the blocks?
Sorry, say again?
For the numerical simulation, is there a continuity on the boundary of the block?
For this one?
Yeah.
Well, this is not a numerical simulation. I mean, you could convert it into a numerical simulation, but yes, you are assuming there is continuity. It's a continuum.
The blocks, there's a continuity one at a higher part, and the boundary are they the same, or how do you?
Well, I wouldn't get into details if assuming this is a numerical solution, but my objective here was just to mean that the rock is heterogeneous and it has slightly different values in all of those blocks. So let's see if we see this. We find this. It's marble, brittle, ductile, and I think it is in the New York Museum of Natural Science. It's a great picture, but okay, well, this is similar to what I wanted to show, but the other one, it's a lot better. I'll find that one. I'll send you that by, oh, here. I think it's this one. Yeah, this one. Okay, well, the quality is not fantastic, but hopefully you get to see over here. This is marble. It is quite brittle in unconfined conditions, and when you start to increase confining, it transforms into a material that is not strain softening with a well-defined failure, but it gets strain hardening with distributed or diffused failure around the rock. And you can see that as you increase, in this case, the mean stress, the material behaves completely different. Something very important to take into account here too is that the notion of breakouts implicitly assumes that you have brittle failure, because you are assuming that there is a well-defined failure plane and the rock is going to fall into the wellbore with the drilling cuts as you're drilling. But if you have plastic deformation around the well, you're not going to have breakouts. You could have plastic failure or plastic deformation around the wellbore, but no breakouts if you are in a ductile or strain hardening mode.
Wait, this is the strain rate?
No, this is mean stress. For example, yes, this would be how this rock fails on surface, and this will be how it fails at 10 kilometers of depth.
So if you increase the temperature?
And that's where now we go to that point, and that's going to be the last thing we're going to see. This is what is called, if we were to make plots of stress versus strain, we're going to see something like this. Triaxial tests, sigma 1 minus sigma 3, deviatoric stress. And here we plot epsilon 1, strain in the direction of the load. We will see that brittle materials fail with a well-defined plane. Let me. I don't know what happened over there. So a material somewhere over here is the one that fails with very well-defined shear fractures. A material over here is a material that gets fatter and has distributed failure, and you can see the progression over there. And this will be as you increase many things. One of those is sigma 3, or mean stress, or as we have been seeing in our formulation before, P prime. Another factor that could make this same transition is temperature. The higher the temperature, the more ductile a rock is going to get. Another factor, do you think about any other thing that could cause this one, this type of what? Heterogeneity, probably, but that's a very general term, heterogeneity. What do you mean specifically with heterogeneity? The what? Maybe, I'm not sure about that, but I don't see it very clear right now. Let me continue with the ones I know. Decreasing the loading rate will also make a rock to seem more ductile. Like, for example, when we were saying folding of geological layers over geological time, over millions of years, a rock that appears to be super brittle over millions of years with creep, with everything inside, it gets a lot more ductile. Another one, very interesting, that I kind of knew about, I mean, not that I knew, but I knew it was out there, but undergrad student recently told me I should include, particularly for shales, is increasing organic matter will also make the rocks to be more ductile. And also increasing amount of percentage of clay would make shales to behave in more ductile manner. And another one which is not very obvious, and I'm going to put it separately here, but also important, is length scale. Oh, it's already 5:30. No, it's not. We're going to stay here 30 more minutes, but I need time to upload my video. Okay. Let's imagine a fractured rock mass with brittle rock inside. And we run triaxial tests on this fractured rock. So let's say we get the sample of that rock, we take it to the laboratory in the absence of fractures, and I'm postulating here that this is a brittle rock. So probably it will look something like this. Very well defined peak stress, and as it fails, very well defined fracture planes. What do you think is going to be the response of a rock which is now a rock that also has fractures inside? And if we load it under deviatoric conditions, do you think it will be as brittle as an intact rock or not?
I think it would be more brittle, the change would be accommodated, or more ductile, the change would be accommodated by,
So what do you mean the changes are going to be accommodated?
I guess, like crushing and readjustment of the spaces that you already have open would allow it to take more stresses, or it adds another fracture.
Let me see if I can draw this in here. So if this is the rock and it has these pre-existing fractures, very likely when we load it in this direction, we might have this top part to move down like this, and this one like to move up relative to each other. We could also have displacement in the other direction, but it's not going to be brittle anymore, because your fractures now are taking that deformation and that failure. Is because of the fracture, it's going to be a lot softer. And if I'm assuming, okay, this is something important too, okay? These are uncemented fractures. If we have cemented fractures, well, then we have one more level of complexity. But if you have uncemmented fractures, these will tend to be a lot more ductile, and will probably just go to this residual strength that we said before, where the strength of the rock is just going to be the strength of the fractures themselves. Okay, I think that's everything I have for today, and I'm just going to mention very quickly three more things. So we finish with plasticity, okay? So 2 more minutes. We have seen something which is called isotropic hardening. And isotropic hardening would mean that in our principal stress space, if this is the isotropic axis and this is my, say, my yield surface, that always the yield surface grows symmetrically around the isotropic axis. And that's a good assumption for many materials, but I just like to mention that there is something else called kinematic hardening, that by making a material fail in one direction, it could preferentially get stronger into that direction, or a direction associated with that failure. And if you had an initial yield surface, let's say like this, and after this your yield surface moves in another position, that is what is called kinematic hardening. And so far what we have seen is isotropic hardening. And the last thing I want to mention is that we have seen also that the yield surface can change due to due to changes of mean stress. Let's imagine now a cemented rock. This is what the yield surface would look like. Notice that it has an intercept here at P prime equal to 0. So this is equivalent to a cohesive strength. And this would be the way that you would model a cemented rock. There is another field of mechanics which is relatively new, in which your yield surface could also change due to chemical actions. So you could go from something cemented to uncemented or less cemented, and when this change is caused by chemical actions, this is a field which is called chemo-plasticity, and it's a very interesting field, because then when you want to model all these processes, you have to couple together fluid flow with transport, with reaction equations, together with mechanics. For example, if you wanted to model couple geomechanics with acid injection, you should consider something like this.
Is anyone in PGE focusing on this?
I'm working on this.
Okay.
Yeah, that's why I wanted to mention.
Okay.
Yes. I have been working on this in the context of CO2 geological storage, and I also started to work this a bit related to hydraulic fracturing with acids. All right, now that's it for today. All right.
Would structural diagenesis fall under that chemo-plasticity?
Yes, because you could have also your rocks doing the opposite, right? Going from a yield surface which is small to something which is bigger as you have autogenic cement precipitation. All right, now I